Hello, this is Phil Stephenson, Senior Geotechnical Engineer with Cathie. I'm delighted to be able to give a presentation today at this webinar, and the subject that I'm going to be talking to you about is geotechnical design and analysis for offshore wind turbines in Korean waters. So this is the outline of the presentation that I'll give today. First of all, I'll just give a very brief introduction as to who Cathie are and what we do. I'll then go on to talk about the offshore conditions in Korean waters in terms of water depths and also ground conditions. I'll then talk about foundation solutions and which would be viable for those conditions. I'll briefly talk about heat mapping and how that tool can be used during the foundation selection stage. I'll then talk about some key foundation types and the geotechnical design and analysis techniques that we use on them. I'll briefly talk about other key geotechnical issues, and then I'll draw together with some conclusions. So who are Cathie? We are a global offshore geotechnical engineering consultancy. We have over 60 staff spread across the world, professionals in geotechnical, geospatial, geophysical and engineering geology professions. We are a company that originally started working in offshore geotechnics to service the oil and gas industry, but since that time and with the beginning of renewables, we've been involved with a lot of renewable projects, and we have as a company got experience on offshore wind farms that generate over 75 gigawatts of electricity and on subsea cable routes a length of over 17,000 kilometers. So with the mix of wide experience that we've got in terms of disciplines and also with the past experience that we have, we can provide a really high quality service in deriving subsea solutions for the offshore industry. So starting the main body of the presentation, looking at Korean offshore developments, we'll start by looking at water depths. So I've taken this image from the 4C offshore website, and it shows the developments in the Korean area, which are either fully commissioned, in pre-construction, or consenting and planning stages. There's 74 registered offshore wind farms in that database, and as you can see, they are spread along the virtual full perimeter of the Korean coast, and also to the south around the island of Jeju. Just interrogating that database to look at water depth, you can see that there's a wide range of water depth, but in particular there's quite a large percentage, 25% of the offshore wind farms are positioned where the water depth is greater than 60 meters. And we'll talk about the what that means in terms of foundation selection in a little while. Going on to talk about ground conditions, I'll illustrate that by just talking about the conditions we've encountered at 4 sites we've recently looked at on offshore Korea. So looking at site A, first of all, it's a site that's to the west of Korea in the Yellow Sea. It has 10 to 20 meters of water depth, and the ground conditions comprise a thin layer of marine sand, which is underlaid by low to medium strength clays and silts, which are normally consolidated and are transgressive deposits from the Holocene area. Underlying that is weathered bedrock, which is granitic in origin, and that's at a depth at about 40 to 50 meters. Moving round to Site B there, which lies between Wondu and Jeju Island. The water depth is of the order of less than 50 meters near the mainline, but gets deeper up to 135 meters as you go towards Jeju. The geology is quite similar to Site A. However, when you get towards Jeju, which is a long extinct volcano island, you get some quite hard volcanic rocks near to or at seabed, which is a particular condition in that area. Moving around the coast to sites C and D here, which are in the Korean Strait and also in the East Sea. The ground conditions are again quite similar. The difference here is that the water depth is more. It's about 85 meters at C and over 100 meters at D. And the depth of the superficial deposits again is a bit more, between 80 meters and 100 meters. Slight difference at Site D is as you approach the coast there is a risk that bedrock also comes to the surface and will comprise sedimentary rocks. So as a whole, the conditions are quite challenging from the point of view of ground conditions. Soft soils, which are not particularly competent for foundations, and then also potentially some shallow rocks, which could be quite challenging. Just in terms of thinking about other ground-related issues, there is a relatively low but existing level of seismicity in the region. Although this is defined as seismic zone 1 in the ISO standard, so will not require a detailed site-specific hazard assessment. Also, with the nature of the ground conditions at the surface deposits, there is also a risk of scour, particularly where the water depth is shallow. So these are two other issues that need to be considered as part of the geotechnical design process. So just moving on to think about the impact of those conditions on foundations. First of all, looking at water depth. So fixed bottom solutions where the wind turbine is fixed to the seabed are suitable for depths generally less than 60 meters, although you can push it to depths that's slightly higher than that. So looking at the sites that we've just looked at, sites A, B and parts of C would likely be suitable for fixed foundations. However, when you move along the Korean Strait and then into the Eastern Sea, the water depths get much greater than sort of 60 meters. Then floating wind farms become probably the only viable solution, and that is the sort of solution that you probably look at for parts of C and also D. So just to think about foundation types beyond whether it's fixed or floating. So from a fixed foundation perspective, you can see 4 options there: monopiles, GBS, pile jackets and suction caisson jackets. And they each have their own pros and cons. But thinking about the conditions in Korea, monopiles has been a solution that's been adopted in other parts of the world quite successfully for water depths of less than 50 meters. The issue with Korean conditions is that there are soft soils and also potentially shallow bedrock, which may cause issues for driving, and therefore monopiles would have to be carefully studied during feed stages to see whether they were suitable. Moving on to GBS foundations, large structures which are sunk to the seabed and are supported on the seabed immediately, and these require quite competent ground conditions. And so given the soft and loose nature of some of the deposits around Korea, it's unlikely that this is going to be a viable option for those conditions. except for a very sort of localized areas such as around Jeju, for example. Pile jackets is a technology for which there's a proven supply chain within Korea, and so it could be a very good option here. It's possible to go to greater water depths than 50 meters with this solution, but the presence of shallow rock may cause some issues and would have to be checked because pile length might be significant in the soft deposits. Suction caissons is a less proven solution than the other solutions we've just talked about, but it could come into play for sites where there is shallow rock that might foul monopiles or jacket piles. One thing that would have to be carefully considered with that sort of solution is the scour, and this solution is quite sensitive to scour. So in terms of the presentation, I will talk about monopiles, pile jackets, and suction caissons as options that could be looked at for Korea. In terms of floating wind, there's a number of different solutions that we could talk about, but for the purpose of this presentation, we're going to look at drag anchors. This is a solution that's been adopted on other floating wind farms and across the world, and for the conditions that Korea is a solution that may be viable. So just moving on from particular solutions, let's just talk about heat mapping, which is a semi-qualitative scoring mechanism that could be used to assess foundation selection on a particular site. So this is a GIS technique whereby the site is gridded and then scores are identified on the grid for each foundation type on the basis of water depth, bed forms and scour risk, quaternary deposit depth and strength, and the presence of obstructions such as shallow rock or exclusion zones where there might be existing infrastructure. Once this scoring procedure has been done, aggregated scores can be produced for a particular site to identify which foundation option might be the better ones to pursue. The heat map charts can also be viewed just to have a look to see whether dual foundation strategies might be suitable for a particular site, such as floating and fixed or whatever, and also to decide on areas which will be excluded from development because of difficult constraints. So it's a very useful tool that can be used. So just to go on to talk about geotechnical design and analysis now, and to start with some overarching principles. So the objectives of foundation design are to provide an acceptable and reliable solution for the foundations over the lifetime of the structure, for the foundation solution to be economic and also to be installable. We do this by looking at a number of things. First of all, we undertake limit state design and look at various load combinations on the structure. So we look at ultimate limit state, so the set of worst case loads, and check that the foundation will be suitable, that there'll be no ground failure and that no catastrophic collapse will occur. We then look at normal loading conditions, serviceability limit states, and check that deflections and natural frequencies of the combined system are within the limits for the turbine. And then thirdly, we look at fatigue limit states, which are lower levels of high numbers of cycles of loads, to check that structural components won't be subject to fatigue damage with constant beating of loading on the structure. As well as the limit state design, we also have to look at the important issue of installation. So we carry out specific installation studies to check that the required foundation dimensions can be installed to the required depths or the sizes that can be produced, and that the equipment that needs to be used to install it, those foundations will be stable during installation process. In addition to that, there are specific other issues that we have to look at. Scour assessment, scouring around foundations and the possible impact that might have needs to be looked at. And also in seismic areas, liquefaction or seismic loading also have to be looked at. So just going to go on and look at the various types of foundations and just talked about the analysis techniques that you use for each. So starting with monopiles. Monopiles are a very slender type of foundation, single large diameter driven pile to support the wind turbine structures. And as a result of that, the deflections of the structures and the rotations of the structure tend to govern, and the response to lateral load is key. And the way that we deal with that is to look at the loads and develop PY curves to look at the stiffness of the ground in response to the lateral load to give the structural engineers information on that. And we'll talk about that a little bit more in a minute. Another key consideration we discussed is installation and drivability of the required monopile sizes down to the depths that are required to achieve stability. That's another aspect that we'll talk about in a second. So PY curves, what are PY curves? So they are lateral springs effectively that are applied to structural models to represent the ground. So they both laterally and also in terms of moments are applied or developed and provided to the structural engineer. So there are codified ways of defining these springs based upon soil characteristics and parameters. But at later stages of a project, then we begin to have to model the complete soil structure system in finite element models in order to more accurately calibrate those PY curves. So the two diagrams here show an example three-dimensional finite element model that's used to model the soil and the structure in one go. And then the results of that are then used to calibrate PY curves that we might have got from codes to the more specific circumstances of a site. So why do we go to the extent of doing finite element analysis? That's because in order to realistically estimate the behavior of the ground and structure, we need to model some quite sophisticated aspects of soil behavior. The first aspect is small strain stiffness. As the ground is initially loaded, it has quite high stiffness, and then as it's strained and the increased loads, the stiffness tends to drop off, and we end up with this S-shaped curve of stiffness degradation with strain. And in the FE models, we used what's different soil models like the HS small strain model in Plaxis to model this, and we developed soil parameters to reflect lab tests on these particular parameters. We also use the FE analysis to look at cyclic loads and the impact that that has on soil deflections, deformations, and we do that by checking what impact the cyclic load has upon the shear strength of the materials, surrounding materials. There's particular ways that we do that, but that is dealt with within the FE model. Okay, in terms of drivability of the monopiles, there's particular procedures we use for this. So resistance to driving is developed in the monopile by end bearing at the base of the pile and then also skin friction down the sides. And there's some well documented and researched methods for estimating what the values of the resistance will be. And what we use those techniques like Alhambra, Stevens and Colliat to do is estimate the skin frictions, end bearings to produce what's called the soil resistance to driving. That is then input into a program like GRLWEAP, a wave equation analysis program, together with the hammer input parameters and the dimensions of the monopile. And from that, we can identify the blow count per meter depth as you go down the pile to drive the pile, and also the maximum stresses and fatigue stress ranges that will occur within the pile during the driving process. And by doing that, we can check for the design level whether or not they all remain within acceptable limits and that the pile can be driven. Moving on to jacket piles. These are quite different to monopiles. The jacket structure evens out the loading of the wind turbine, which causes the loading on the piles to be vertical predominantly rather than lateral in terms of the governing cases. So axial pile capacity is a key issue here. We do have to check lateral pile capacity and look at cyclic loading as well, and we do have to undertake drivability assessments as well, but axial pile capacity is one of the main issues. So in terms of pile design, pile capacity is developed from shaft friction, but also tip capacity. The latter, tip capacity, is dependent on whether the pile's plugged or unplugged. And there are standard methods for dealing with that in the API main text. But they can be quite conservative, and there are other methods that can be used which are based upon in situ testing, such as CPT testing. The aims of the analysis are to look at different possible pile depths and the pile resistance that would be developed based upon those equations. And this can be matched against the loads from the structure to define what the pile lengths need to be. As mentioned, we also do need to look at lateral pile capacity, and this is information that's passed on to the structural designer to input into the structural models. Part of that is PY curves, horizontal loads to deflection curves for the piles, standard codified ways of working out this information, and we use an in-house software called AllPile to do that. We also need to do the same thing for the vertical stiffness of the pile. We define TZ curves to identify how quickly the skin friction develops as the pile is deflected downwards, and also QZ curves to define how quickly the end bearing is developed as it's deflected afterwards. We use the same software to develop those curves, and they're passed on to the structural engineer for their models. In terms of axial pile design, we also need to check cyclic loading, because that can also have a degradation effect on the strength of the soil and the pile capacity. And what we do is we break the loads down into the cyclic load down into a series of wave packets of varying load magnitudes and numbers of cycles. Those are checked on a pile interaction chart, like the chart in the middle of the slide there, and this checks average load and cyclic load and assesses how much damage occurs per cycle within the cyclic loading, and that damage can be summed and accumulated to work out the overall degradation in pile capacity over the lifetime of the storm or the structure. Okay, moving on to suction cans. First of all, just deal a little bit with what a suction can is. So it's an open-bottomed caisson which is brought to site and the foundation sunk under its own weight. It penetrates the ground to its own weight, and then the inside of the can, once it's been sealed off, the water is pumped out to create suctions within the inside of the can, which help then to pull the can down deeper into the soil deposits below. And this has the effect of producing an embedded shallow foundation effectively. And this can be used for wind turbines either in a jacketed situation with a sort of tripod type arrangement of suction cans, or alternatively with a monobucket, although the latter is less often used because you get quite big buckets. In terms of designing these, you'll have to look at in-place capacity. You have to also look at whether the suction cans can be installed, and it's really important that that's looked at an early stage, because that can be really critical in determining whether this is a feasible solution. And finally, you have to look at scour with the solution. It's it's scour sensitive, and often protection measures are needed with the solution. So first of all, just talk about in-place capacity, and the first stage during early stages is to look at envelopes of capacity of the foundation in terms of the vertical force, the horizontal force, and the moment that's applied to the suction can. And this is determined using conventional bearing capacity theory, but which is then translated to the reference point at mud line by using the relationships which are at the top of the slide there. Once this is done, this produces a series of envelopes which relate moment capacity to horizontal and vertical capacity. And what you do is you plot the loads from the structure to see whether they lie inside of those capacity envelopes, and therefore you've got an acceptable solution. And we use in-house software Caisson to do that sort of study. Once you've gone through the initial study of doing that and developing the solution, the size of the caissons, you then would probably go on to do more bespoke finite element analysis to look at more specific ground conditions and soil behavior. And that's what you would do during detailed design. Moving on to installation assessments. Really critical for suction cans that you do these as early as possible. Similar to pile driving design, you have tip resistance and also skirt resistance, and you've got various methods using both conventional mechanism type approaches or using CPT correlations to be able to estimate what the resistances are to the suction can being driven into the ground. Once you've got those resistances, you can work out what the depth of embedment would be for the suction can under its self-weight, and then you can determine what level of suction pressure is required to then drive it to the depth you need. You check those suction levels against cavitation limits or the limits of the pump to see whether it's possible. And this really does drive the dimensions of the caisson in terms of its aspect ratio between diameter and skirt lengths. And you can see some ratios there for clay soils and sandy soils which generally apply. Okay, moving on to floating wind concepts. These are quite complex structures, usually requiring water depth of greater than 60 meters. They've got 6 degrees of freedom when subject to metocean loading. And when you look at these structures, you have to model the whole structure, turbine, floating raft, and then also the mooring lines in order to get an idea of how it performs and make sure that it keeps station, that the accelerations at the nacelle level will be within acceptable levels, and that the mooring lines won't move around and clash with other cables or other existing infrastructure. So we're just talking about drag anchors as one mooring solution for this type of structure. The drag anchor composes a chain and a drag anchor. The chain is critical to the stability of the structure and lies in the water column and can be up to 1 kilometer long, and is usually patterned in some sort of radial pattern as shown on the slide there. At the end of the chain is the mooring point with a high capacity drag anchor holding the load. The drag anchor is usually preloaded to prove the capacity of it to a certain degree. So in terms of design, the initial stages is to look at anchor manuals, which give charts to show what kind of weight of anchor is required for different drag force requirements from the structure. And that gives you the initial size of foundation. And then as you go further into design, you'll look at kinematic equation methods, which look at the trajectory of the anchor as it's pulled into the ground, how the force develops on the anchor, and also what resistance is developed by the chain, which is submerged beneath seabed level. This is particularly important when you've got mixed soils where the charts from the manufacturers break down. So you have potential drag lengths for these anchors of 200 meters and potential penetration depths of something like of the order of 20 meters. So you can see how important it is to do these calculations and understand what that is before you get to site to construct them and install them. Okay, just to conclude and wrap up, this presentation has given an overview of the issues for geotechnical design for offshore wind farms in Korea. There's a specific set of conditions for Korea. Water depths can range from relatively shallow to quite deep, and the ground conditions are quite challenging, comprising soft, normally consolidated clays and deposits. Although in some areas rock can be quite shallow and could cause problems from an installation perspective. From the presentation you can see that off the western coast and southern coasts, fixed foundation solutions such as monopiles, pile jackets and suction caissons could be potential options, whereas off the eastern coast where waters are very deep, then floating foundation solutions become the only real viable solutions. Gravity-based structures were discussed as well, although they're probably less likely to be applicable in the Korean conditions. The use of heat mapping as a semi-quantitative method for foundation selection for a particular site was discussed. And then we went on to the real meat of it and talked about different geotechnical design considerations and analytical techniques for different foundation types. We didn't really have a lot of time to touch on other geotechnical issues, but scour and seismic issues such as liquefaction and seismic loading also have to be considered. So all that leaves us to do is just to thank you for your attention and to hope that you enjoyed the presentation and found it informative.